Thank you. So today I'm going to talk about physical processes in organic solar cells. And we're going to start with a brief introduction, our motivation, the main goal. Then we will turn to the main part, which is the modeling and the experimental part. I will show you our measurement setup, and then we will talk about Bilayers, which are very simple architecture of organic solar cells. This part will be based on a paper that we published with a model of these Bilayers. Then we will talk about charge dissociation mechanisms. Also, this part is based on a review paper that we wrote about charge dissociation mechanisms from the last century. And then we will talk about our model of this dissociation, which we published. And then we will talk about our last publication about the SRH recombination or trap-assisted recombination, and then we will conclude. So when I'm telling people that I'm working with organic solar cells, what they think is that I'm trying to produce electricity out of chloroplast, or that I'm doing DNA computing. However, both of them are bioelectronics. Organic electronics is based on organic materials which contain carbon and hydrogen. And you can think about these materials as rubbers or plastic. Here is an example for the well-established organic technology, the Oled Displays. You can see that they can be flexible and also transparent. And here, this is an example for a company who tried to commercialize the organic solar cells and also succeed. There are not so many companies in this field, and the efficiency is still low. However, they had several big projects. This is an example for the last big project they've done. They covered up this roof in Berlin with their solar cells. Now, why to do organic electronics? So first of all, it's cheap. All you need in order to start is a spin coater, glove box, and evaporator, and not a fancy or expensive fab. And also, as we've seen, the devices are flexible and low weight. And there is basically almost an infinite number of organic derivatives and polymers. So there is chemical tunability. And also, they can be biocompatible. However, there are disadvantages as the poor mobility. We will see later why the mobility is so poor. And of course, it's affects badly on the efficiency. And also, these materials are excitonic materials, which means that when we shine light at an organic solar cell and we form the electron-hole pair, then it's very hard to break it or to dissociate it. So also this have a bad effect on the efficiency. Here are some more organic devices, for example, organic memories and the OFATs. And now to our motivation. So here in this graph, you see the power conversion efficiency for all types of solar cells, how they developed through time. And these red dots here are for the organic solar cells, approaching today to about 20% of efficiency. And in order to get to this point, and in order to continue and improve, one should gain a better understanding of the physical process in this organic solar cells, and this is our main goal. So now a brief introduction about Biliary devices. So as I said before, Bilayers are very simple architecture of organic solar cells. It's look like the PN junction, although it's different. So what we have here is two active layers sandwiched in between two electrodes. And with a closer look, when we apply light, when we shine light at the device, then we form an all-electron pair that we call an exciton. Now, this exciton has a short lifetime. However, with the right design, it would diffuse to the interface, and one of the charges would transfer to the other layer. And we call this new species CT, or charge transfer. And the layer where we will have the electron is the acceptor, it accepts electron, and the other one is the donor. Also, this CT is tend to decay very quickly. However, with a smart design, it will dissociate between before decay, and we will get two charges that we call polarons. One would be negative, the other one is the positive one, and we want to transport them to the contacts. However, as I said before, the mobility is very poor, and this is because these materials are molecular conductors, which means that although it may be relatively easy to mobile the electron on a molecule, it will be difficult to make him to jump between molecule to molecule, and it does it by means of quantum tunneling. And we call quantum tunneling in organic electronics oping. So this process is very unlikely, and therefore the mobility is poor. However, we managed to collect transport the polarons and to collect them with the contacts, and then we will get the desired current. So the desired processes here is to absorb light, form excitons, then the excitons should diffuse to the donor-acceptor interface, create a city. The city should dissociate to two polarons, and then we will would transport and collect them to form the current. However, there are always loss mechanisms as exciton decay and city decay and recombination of polarons back to cities or back to the ground state. Now, why to use bilayers and not, for example, single layers? So basically, the driving force in these devices to charge dissociation is the electric field, and in singular, it's spread all over the device, and it makes it difficult to dissociate a local city. However, in the bilayer, we have this step here, which helps the charge dissociation. And also, it prevents, once we have city, it prevents it to go back to form the exciton. Therefore, we don't have this process here, but we have it in the singulars. And in modern devices, we are using the architecture of bulk heterojunction or BHJ, where we mix together both active layers in order to get larger areas of interface, and also to suppress the exciton decay, because wherever we're going to absorb light, there will be always an interface nearby that the exciton can diffuse to before being decayed. Now, this is our measurement system, which is very important in our modeling process. And by say modeling, I mean to build a model, not only to fit parameters, but to find the right and the main processes that shed light on the device physics. And therefore, we must have for this modeling a solid ground of measurements of real devices, and there is a constant ping pong back and forth between the modeling and the measurements. So this is the measurement system I assembled. Everything is controlled by the computer here. We have the white light source and the motorized filter wheel. Together, they form a light source with 6 orders of magnitudes of illumination up to 10 solar intensities. And we control also the temperature in the range of 100 to 300 kelvins. We control this Kitli, which force bias on our devices while measuring their current. And all this prop station is evacuated by this primer and turbo pumps. And I wrote this user interface in LabVIEW in order to control the system in method of fire and forget. So we put all the parameters here. We click run, it runs for several hours. We will go to lots of raw data. In order to analyze it efficiently, I wrote this GUI in MATLAB, which helped us to calibrate the system and also to plot graphs that I will show you later on. So now to the modeling of bilayers, which was published here. So as I said, actually in these devices, we have 3 species, the excitons, the cities, and the polarons. And we should ask ourselves, what are the relations between them? What are the main processes govern these devices? And in order to do so, first we must have a good measurement, as I say. So we measured the J versus V, JV in dark. We measured the J versus V for 5 order of magnitude of illumination. And we measured the light intensity dependent quantum efficiency for multiple biases. Now, what is the quantum efficiency? So when a photon hits our device, it should generate an electron in the external circuit. However, because of losses, sometimes there is a photon that won't create any electron. And basically, the quantum efficiency is the ratio between electrons in the external circuit versus the photons hitting the device. Okay, we measured 4 types of bilayers. In all of them, we used the same acceptor, the C70, which is a Folaran, and we used the 2 types of donors, the TAPC and the C70, and 2 types of HTLs, all transport layers, the P.PSS and the CUSCN. All transport layer is actually a step that improve the whole injection between the anode and the donor. So we have 2 types of HTLs and 2 types of donors. So it's 4 combinations for devices. Here you see an example for the results for the TAPC-C70 devices, both with the CUSCN and the P.PSS as the HTLs. The dots are the measurements, while the solid lines are the fit that we done with our model. So this is the result of the modeling and the fitting processes. So it seems that we have a very nice model for these systems. So you must ask yourself, what is your model? So this is the processes that I used here. And I want to emphasize a few things here. So we find that for the polar recombination vector city, we should use a bimolecular recombination or Langevin recombination, which is basically a collision between hole and electron. We found that the polaron's recombination to ground state is basically due to SRH process, which is a assisted recombination. And we was very glad to find that this is the process here, because it seems that the SRH traps are not directly related to the charge generation. Which means that maybe with a smart design, one can get rid of these SRH traps with minimal damage to charge generation. Also, I want to emphasize this process here, which is thermal formation of cities, which is not important at all when we shine light at the device, even very low light intensities. Because basically when we shine light, then all the cities form due to this optical excitation. However, in dark, when there are no excitons, this process is what keeps the current to be 0 when we apply 0 bias at the device. Why? Because in dark, when we apply 0 bias, we basically at equilibrium. So all these processes are in detailed balance, and we can eliminate them. And then the only thing that balance the CT decay is basically this process. So this process is important for our model, not only to restore or reproduce the behavior of the device under illumination, but also in dark. So it's very important for the self-consistency of the model. So one rule of thumb we had when we modeled was self-consistency, and the other one was to keep things simple. And therefore, we use the model of rate equations instead of model of differential equations. And also to keep it simple, we put a lot of effort in finding the minimal set of processes that can reproduce the behavior of the device. And this is the minimal set in this case. So we have 3 rate equations, one for each species. And we had also this equation, which gave us the relation between the polaron density under the contact and near the interface. Now, we also did this measurement in order to confirm our model. This measurement is not related to our modeling process or fitting process, and it's a measurement of the quantum efficiency versus the photon energy, not versus the light intensity as before. And we can learn from this measurement something about the shape of the energy bands. So we see that for both devices, the CuPCC70 and PAPCC70, there is a tail of states inside the band gap. And we extracted the properties of these tails into this table here. And also we have a second table of parameters, of the fitting parameters from our model for the same devices that related to the SRH traps. And what we see is that in both tables, there is the same trend that the subject state or the SRH traps in the CuPCC70 device are deeper. And also the total number of subject states or of SRH traps in the TAPCC70 device is twice than in the other device. So maybe the numbers are not exactly the same, but we were very pleased with this result because we need to keep in mind that this model is very simple. It's only a rate equation model. And also when we model the SRH traps, we used only one energy of trap. So the distribution is like a delta function and not a Gaussian distribution. Now we will talk about the charge dissociation mechanisms. So we are going to talk mainly about this process, although we are going to talk about other processes related to the city. And we are going to talk them also in bulk heterojunction devices. And this part, as I said before, is based on our not yet published review paper, and it will lead us to our model about the charge dissociation. So what was the motivation to this work? So in the first work that I showed you before about the bilars, we basically modeled the charge dissociation by using Onsager-Brown model. And we wasn't the only one to use this model. This model was very, very popular in our community. And Brown suggested this model in the 80s, which were the first days of organic electronics. And he used the Onsager work from the 30s and add several things to it. So here we see is dissociation constant. And this ratio here with this Bessel function is basically from the original work of Onsager, and this exponent with the binding energy is something that Brown had. And yes, we managed to fit this binding energy to all the 4 devices I showed you before. However, we asked ourselves why this binding energy should vary between these systems. What is the real physical meaning of this binding energy? And we couldn't find a good answer. Also, we know that in organic materials, there is an intrinsic energetic disorder. Why? Because each molecule in the bulk looks a bit different. It's as a different conformation. One may look like this, the other one like that, the third one like this, and one is maybe near the contact while other one is near the interface. So each molecule here will have a slightly different energy, and there is basically a distribution of states that we can model as a Gaussian distribution. And all of this energetic disorder does not appear in Onsager-Brown model. Also, what about spatial disorder, חוסר סדר מרחבי? Because we know that all of these materials are not crystal, they are not periodic and ordered, but they are molecular conductors and the molecules entangled. And also the medium here is discrete because the polaron jumps or hops between molecule to molecule, between side to side in a discrete way. And also where this ugly Bessel function is coming from. So in order to answer all of these questions, I go back to Onsager's original work from the 30s, and I read it once and twice, and the third time, and I couldn't understand anything till we encountered this biography of Onsager. So let's read. Yet it was not only students who found Onsager difficult to understand. His colleague had the same difficulty. And then I understood, okay, so I wasn't the problem. But of course, Onsager got his Nobel Prize, so we need to be a little bit modest. So after I read it again and again and again, and I used a different work of others to try to understand Onsager before me, we managed to understand the physical picture he depicts in his model. And we need to think about a salt or nuclei of a salt that we dissolve in a solution. So these are the ions in the solution. And what we try to do is to find the electric field dependent of the distribution of bonded ion pairs in this solution. So when we change the electric field, we change also this distribution. And the variable here is this F, which is the distribution of bonded ion pairs. And the electric field he used was the external electric field, as in here, plus the electric field of Coulomb interaction. And this is the shape of the electric potential used. Use the drift diffusion term and the continuous equation equal to 0 because we are in steady state, and these two boundary conditions. The first one basically says that a pair with infinite separation is basically free. And the other boundary condition says that this nuclei is at equilibrium with his immediate environment. Or in other words, that this nuclei serves as a source of fixed density. So the ion's density all around it is fixed. Now he managed to solve this equation, very ugly solution. For me, it took, in order to reproduce this solution, it took about 30 pages of calculations. But it was very nice to see that when I'm taking the external field to be 0, so basically we're at equilibrium, the distribution of pairs is basically the Maxwell-Boltzmann distribution. But this is not the end, because what we want to find is the dissociation rate. So we need to use again the drift diffusion term in order to find the flux of dissociating pairs. And then in this system, because there is balance between dissociation and combination, Onsager was able to find this A0 here, and also he found the ratio between dissociation rate with and without apply of external electric field, and he found it to be this Bessel function. Now, 4 years later, Onsager suggested different model for different system. Here, the source is not of a fixed density, but of fixed generation rate. And also the pairs have initial separation of R0, which is not necessarily 0. The pairs may dissociate or go back and recombine like this pair. And he used the same type of electric potential. And these are the equations here. So let's compare between these two models. So in the first model, the variable was the pair density, while in this model, the main variable is directly the dissociation efficiency. Also, the source then was of fixed density, and here is of fixed generation rate, and not necessarily 0. What about the boundary conditions? So the first one basically says that when the separation of a pair become to be 0, there is no chance for dissociation. And when the separation of a pair become to be infinite, so there is no possibility for go back and recombine. And also in Onsager 34, there was balance between recombination and dissociation, while now recombination and dissociation together should balance the generation. So we can say in 2 words that Onsager 34 was designed for ion chemistry, while Onsager 38 was designed for optical excitation. So if we need to choose one of them in order to model organic solar cells, I would pick the Onsager 38. However, when we go back to Onsager Brown work, we see that Brown based his model on Onsager 34 without a good justification. Now, these two works of Onsager are for ordered system, because this is the electric potential used with its order. There is no electric and energetic disorder here. The medium is continuous as for semiconductors and not discrete as for molecular conductors. And also the medium is isotropic, so there is no place here for any kind of donor-acceptor interface. Now, in the same time that Onsager suggested his second model, also Frankel suggested his own model to the same system, but with a different scenario. So he used the same electric potential only for the 1D case. And he said very simple thing. He said that in order this electron to detrap or dissociate, it does it, the probability for this electron to detrap or dissociate is basically proportional to the exponent of minus the energy barrier here. So while Onsager used all the shape of the electric potential, Frankel used only 2 points here of this potential, the energy barrier. Okay, it's very simple. So several researchers used the Onsager 38 in order to model their devices, while the other ASCOL used the Frankel. However, when we look at the Onsager Brown model, we see that this part is from Onsager 34, while this part with the binding energy here is like the Frankel. And both of these parts are for not the same scenario, so the model is not self-consistent. Now, as I said before, Onsager 38 and Frankel models was for the same system, but with different scenarios. So here is our contribution in bridge this gap between these two models. So first we need to take Frankel model and to expand it. So we need to add the probability of detrap, also the probability to go back and recombine. And also we're gonna add some steps in the way that we can dissociate or detrap from each state to the next state, or we can recombine to the previous state, and all the transition rates here are according to the original work of Frankel. And what we found when we plotted the dissociation efficiency versus the initial separation is that it's not so matter what is the spacing we take between these steps. The picture is always converge very nicely with the 1D analog of the Onsager 38 model. And we think it's a very nice picture. Actually, this extended Frankel multi-step model has its own name. It's called Rubel model. So Rubel model is 1D model, a discrete model that one can find very easily the transition rates here if he knows the energies of all the sites. And it's also very easy to calculate the dissociation efficiency. All you need to do is to formulate this set of rate equation, one equation for each site here, to solve the system, and then it's very easy to find the dissociation efficiency. And because this model is so simple, it's also very easy to expand it. So by adding this exponent here, we may introduce to the system a spatial disorder, like you see here. When all the spacing was uniform, so this exponent was part of the μ0, now we need to take it out, and basically this exponent is the probability for the tunneling between sites. And we also can add the energetic disorder, Gaussian distributed energetic disorder, only shift the energies, recalculate all the transition rates, and you have energetic disorder. So it seems that this Rubel model answers for almost everything that we want from model of organic devices. It's discrete, anisotropic, disordered. The only problem is that it's for 1D. So it's very tempting to try and expand it to 3Ds. And what we are going to see is that it's very complex to do so. And we will have to do some assumptions in the way. And this will lead us to our EED model. So let's do it. So as I said, we want to expand Rubel model to 2D, for example. All we need to know is the energies of all the sites here. And then we can calculate the transition rates between the sites. And it's look very ugly. And only think what will happen if we try to do it for the 3D. So it's very complex. And we are going to simplify it by using thermodynamics or entropy considerations. But before doing so, I want to emphasize that all of these transition rates that you see here are correct only if the electron locates here. But if we will move it there, for example, then we will need to recalculate all the transition rates because now the column interaction is slightly different. So what I'm trying to say is that these transition rates are basically a function of pairs of sites or pair configuration and not for a single site. And this pair configuration is what we call in thermodynamics a microstate. Okay, so in order to analyze, to do a full analysis of the system, we need to find all the transition rates between microstates, and it's very complex. So what we are going to do is to group some of these microstates in groups that we called macrostates, and then we only need to find the transition rates between these macrostates, and this is much simpler. So in this example, we group the microstates according their color, but in the real world, we are going to group them according to their separation. So let's do it together. So for example, for the separation of nearest neighbors, we have only one microstate in this macrostate, both for the full 1D system and for the 2D system. So basically, the energy of the macrostate are going to be the same as for the microstate. When we increase the separation, so now we have two microstates for this macrostate in the 1D system, and for the 2D system, we're going to have 1, 2, 3, 4, 5, 6 microstates in this macrostate, and we should group them together. So we group them by using this partition function. When this epsilon here is the internal energy of each microstate, and we group them by this summation, and then we can calculate the Gibbs free energy of the macrostate. Okay, and you can think about this free Gibbs energy of the macrostate as the equivalent of the internal energy for the microstate. So this is how we're gonna calculate the transition rates between macrostates, that just do it with the Gibbs free energy and not the internal energy as before. So basically, this is what we are doing. We're gonna find the Gibbs free energy for each macrostates, for each spacing. We're gonna find the transition rates between all the macrostates. And then it's very easy to find the dissociation efficiency because we already know how to do it, because this is basically a Rubel model, which is a half 1D model. Why half 1D? Because one charge here is static while the other can move. It may dissociate or recombine, whatever. And basically what we did here is to reduce the dimensionality as it's written there. We took a 3D or 2D or full 1D system and we converted to half 1D system, or projected the physics from there to half 1D system. Okay, so we need to keep in mind that all of these thermodynamics considerations are only an approximation. And we wanted to find the quality of this approximation. In order to do so, you need at least once to do the full analysis for the system, but it's very complex to do it to the 2D or 3D cases. and therefore we did it only to the full 1D case. And this is what we got. So this is how the full 1D system look like when we try to analyze it. And then we projected the physics from the full 1D on the half 1D system by using all the considerations I showed you. So what we got is that the dissociation efficiency versus the electric field in this picture is both for pure system of full 1D and half 1D, before we used all the thermodynamic consideration. After we projected the physics from the half 1D or from the full 1D on the half 1D system, we got this picture, which is a match. However, this is the picture only for the ordered case. When we introduce this order to the system, then the pictures wouldn't match anymore. And we asked ourselves why. And the answer is that while doing all this thermodynamics consideration, we assume equilibrium, because basically what we have here is Boltzmann exponent. And in our system, there is no equilibrium because we always shine light at our device. And already Onsager told us that we can't use equilibrium because it was very easy to use equilibrium. However, he did all of this very hard calculation, which took me 30 pages. And what I'm trying to say is that the thermodynamics cannot depict, it cannot catch all the dynamics of the real system. However, what we claim is that this mismatch is appear mainly in 1D systems. Why? Because when we introduce this order to a 1D system, then we destroy all the odds for these charges to dissociate. They have only chance to go back and recombine. So this system would shift very easily from equilibrium when we introduce this order. However, for 2D, and of course that's for 3D system, even when we introduce this order and we damage a few passes for charge dissociation, there will be always other passes for charge dissociation. So we think that we assume that for 2D and 3D systems, we can use these approximations of thermodynamics. And based on this assumption, we suggested our model for charge dissociation, the EED model. EED is effective entropy disorder, okay, which was published here. So basically, our model was based on a Kassel et al. Model. In their model, they forced one charge to move only on one axis. So they grouped together all of these microstates with the same separation to the same macrostate. In our work, we expanded it and we enabled both charges to move anywhere. So we grouped together all of these microstates into the same macrostate. And also we introduced disorder to the system, a Gaussian distributed disorder. And it means that we draw an energy shift for each site here due to this distribution. And we got a disordered landscape through which the pair may dissociate. Okay, and we were able, by using all the thermodynamic consideration I showed you, to calculate the Gibbs free energy, half 1D free Gibbs energy for this disordered landscape. However, in a real device, we have lots of cities, lots of sites that cities can dissociate through. In each side, there is a different disordered landscape. So we need to redraw again and again the disordered landscape. And for each one of them, we need to calculate its own local Gibbs free energy. And then we should somehow to average all of these local systems in order to find the effective behavior of the device. So what Kassel et al. Did, they say that it's very simple. You need only to average the local Gibbs free energy in order to get an effective one for the whole system. And this is the result they got. They found that whenever they increase the amount of disorder in the system, or they increase the width of the Gaussian distribution of disorder, then they lowered the energy barrier for charge dissociation. And basically here they got even zero, not a energy barrier at all. And I think that it cannot be true. So what I suggested in our model was do not average the Gibbs free energy, but for each local free Gibbs energy, first translate this free Gibbs energy to a local dissociation efficiency by using, for example, this Rubel model that I showed you, or any other method. And then we should to average these dissociation efficiencies in order to get the effective one. And why this is the right way to do it? So I think it's a good lesson for us that when we're trying to model a system, we need first to think what we are really measuring here. So in order to find dissociation efficiency of a solar cell, what we measure is the photocurrent. And let's have a look at this city here. So in case it's dissociate, it would contribute to the photocurrent. However, if it recombine, it won't contribute to this photocurrent. And the contribution of the city to the photocurrent is proportional to the local dissociation efficiency of the city. And because we have a lot of cities here, each one of them is going to contribute as proportional to its own dissociation efficiency. The overall photocurrent here will be proportional to the average of local dissociation efficiencies. Okay, and this model also gives answer for the dimensionality that we need.